When we describe a motion without telling the causes of this motion, that is called kinematics. Now, dynamics is a description of motion accompanied with forces, and Newton's second law is one of its applications. In Newton's second law, when a net force acts on an object, it gives an acceleration, and this acceleration is directly proportional to this force and inversely proportional to the mass of the object. What does net force mean? When we say net force, it means we are considering several forces actually acting on this mass, and the vector sum of it is the net force. So the vector sum gives us a result of m multiplied by a, where m is the mass of the object and a as a vector is the acceleration of the object. It is important here to note that the direction of acceleration is related to the direction of the force. So when you specify the direction of a force by an angle, you expect that this acceleration will get the same angle. To get an acceleration, simply, if you have the net force, divide that by the mass, you're going to get the acceleration of the object. Here we're going to talk about Newton's second law and the relation between the acceleration and the force with the absence of frictional forces. So this girl is going to push the cart with her force of F to give the cart an acceleration of A. If she doubles her force 2F, then the cart will move with an acceleration of 2A as long as the cart having the same mass. Obviously, if she triples her force, the expected acceleration of the cart is 3 times. Here, if she keeps her force in the first case as is with F and having a mass of 1 cart, we expect an acceleration to the cart of an A. Now, if she's going to push 2 carts with her force F, what do we expect the acceleration is going to be? As long as the masses become double, then we expect the acceleration to become half of the previous one, because the acceleration varies inversely with the mass when you keep the force constant. Now again, a cart of mass m has a pushing force on it of 1 Newton, gives it an acceleration of 2 meters per second square. When this force is doubled to 2, the acceleration of the cart becomes 4 meters per second square. Now if you double the previous force, this force, instead of 2 we get 4 Newton, we expect to get an acceleration of 8 meters per second square to the same cart. Again, the acceleration is directly proportional to the force, and it is in the same direction of the force. In all these cases, friction forces are neglected. As we know, there are two systems for the units, and the first one is the international system that is called Système International in the French language, and the abbreviations come from there. And for the mass, we're going to use kilogram, where for the length meters, and seconds obviously for the time. So one can see that Newton is expressed from the definition of the force as a kilogram meter per second squared in terms of the fundamental units. In the British system, this is the second system we may use. The force, the unit of force is pound, and the unit of the length is foot, while the time is seconds. The mass in this system, the mass is slug, and the slug is the force divided by the acceleration, obviously. That is 1 pound, one slug is 1 pound divided by foot per second square. We know that the mass is a measure of inertia. To understand the inertia, we're going to take 3 cases in here where the force acting in the 3 different experiments is the same force of 2 Newton. And then by applying a 2 Newton force on a mass of 1 kilogram, we got an acceleration of 2 meters per second. We're keeping with the same force but doubling the mass, we're going to get a less acceleration. And then increase the mass to 4 kilogram, keeping the same force, we're going to get an acceleration of 0.5 meter per second square. What does that mean? It means that the mass in each case resists the force or resists the motion that the force is trying to make. By increasing the mass, as we can see, the acceleration is reduced in certain proportion, depends on the value or the magnitude of the mass in each case. So from here we conclude that applying a constant force on different masses shows the ability of each of these masses to resist motion.
When this large rock is struck with a hammer, it barely moves. Why does this rock behave so differently? The first rock is real and very massive. The force of the blow barely accelerates it at all. The second rock is made of low-mass foam rubber. The same blow from the hammer on this rock causes a very high acceleration.
A simple application to the concept of inertia, you can find it in this problem. Here, a force is applied on a mass m1, produces an acceleration of 3 meters per second. When the same force applied on a second object of mass m2, it gives an acceleration of 1 meter per second square. What is the value of the ratio of the mass m1 to m2? This is B, this is A. Part B, if these 2 masses are combined together, what is the acceleration under the action of the same force? By quoting the information we have from the problem that the first mass M1, when the force acts on it, gives us an acceleration A1 of 3 meters per second square, and the second mass under the action of the same force gives us an acceleration A2 of 1 meter per second square, then to find the ratio of masses, simply write the first equation for the first object. That is F equal 3m1, where the acceleration of it is 3 meters per second square. And for the second one, where the force equals m2 multiplied by 1, the acceleration of the second object. Then from these two equations, simply take the division of 1 by 2 to get m1 by m2 equal 1/3. Now, to find the second part of the problem, at part B, the combined masses under the action of the same force will have this equation. Now, we have m2 equal 3m1 from our results in A. When we substitute that into equation 3, we can get that the force equal 4m1 times A. From the first equation, we have F equal 3m1. And from this equation, the latter equation 4, when we solve these two simultaneously, we're going to get an acceleration of 0.75 meter per second square. And this is the answer for part B. As you notice, when we combine the masses, the acceleration is reduced in the second part.